Question 3, we are given a table. So the question says iodide ion is oxidized in acidic solution. Maybe let me zoom in a bit so that you can see clearly. So iodide ion is oxidized in acidic solution to triiodide ion by hydrogen peroxide. A series of 4 experiments was run at different concentrations, and the initial rates of I3 formation were determined. So from these data, obtain the reaction orders with respect to the three different reactants we are given. Okay. So you know that most of the questions, if you've watched some of the videos, most of the questions we've answered before basically get to focus on the idea of two different reactants. Now in this case it was a unique because we have got 3 of them. So reactant 1, 2 and 3, and then they want us to find the reaction orders. How do we go about it? So let's basically handle it. So just like we do in the other kind of questions, we have to observe experiments where 2 of the other reactants are going to be the same. Okay, before that, let's come up with a formula for the electro. So the electro is expected to be R, denoting the rate to be K, multiplied by the concentration of all the reactants. Okay, iodide, and then H plus. Now all these are supposed to be raised to certain powers, so we'll call them X, Y, and Z. Let's call them that. So let's try to identify the experiments where we can see that any 2 are constant. So if I look at experiment 1 and 2, I can see that iodide is constant, so is hydrogen ion. But the other one was what? Was changing. So we can start with that one. So where do we have bigger values? I can see that in the second one, the values are bigger. So we'll start by the rate, since the equation starts with the rate. So we have 2.30. I'm going to be substituting in this equation that I've come up with. 2.3 times 10 to the power negative 6 is equal to K. Now you can see that first of all we've got H2O2. So I've actually arranged them in the same order. So therefore we have 0.02. I'll be removing the last zeros, they're not significant, to the power X. And then for iodide it was 0.010, the power Y, and then for the hydrogen 0.0005, the power Z. Okay, that is for experiment 2. Now we're going to divide by experiment 1. So for the rate for experiment 1, we had 1.15 times 10 to the power negative 6 equal to K, and then 0.010 power X, and then we had 0.010 power Y, 0.0005 the power Z. So you can see that everything else was the same except for this part. So the K and K will divide, this and that will divide, give us 1, that will also divide. That's the actual point. That's why you are basically trying to ensure that you basically get to find cases where the other 2 are the same. So you realize that if you divide what's on the left, so 1.15 into 2.30, that's going to just give us a 2. Now this time is divided by that. Since we've got the same powers, we can actually group them, divide them, they'll give us a 2. We'll maintain the power, so 2 to the power X. So from indices we know that X therefore becomes 1. So that's a reaction order in respect to the first reactant. So that is a 1. So X is equal to 1. So we can now move. Let's try to identify a different experiment now where you can see that they are the same. So if I look at experiment 1 and 3, can see that the first reactant is the same, second one was changing, third one is the same. So therefore we can use that one to find the reaction order in respect to the iodide, which was not the same. So divide, of course, experiment 3. Experiment 3, the rate is 2.30 times 10 to the power negative 6 equal to K. Now at this point, as a student, you have to be sharp. At this point, you already know that the cases where they are the same, they are automatically going to divide. Okay, so this part will come and divide, so that part come and divide. So we'll just leave out the part which will change. That is for the iodide, that would be 0.020. Now iodide, be careful, is raised to the power y. Okay, divide by the first experiment, 1.15 times 10 to the power negative 6. Equally, we'll just consider the iodide, which was now 0.010, the power y as well. So of course that gives us a 2 on the left. K will of course divide. That will give us now a 2 to the power y again. So you can clearly see that even in this case y still becomes 1. Okay. And then finally we can look for the other case where the other experiment, where the other two, the first two are going to be the same and then the other one may be different. Well, for the third one, it doesn't really matter. Even if you find a case where there's no that case, you can just get any experiment, any two experiments, and then substitute the values of x and y. Okay. Alright, so let's consider if 1 and 4. 1 and 4, you consider that we've got the last one actually changing, yet the first two are the same. So equally here we'll consider just the rate, actually the unique part is the rate are the same. So we'll say 1.15 times 10 to the power negative 6 representing experiment 1. I'll only consider a case which is changing, which is that one. So 0.00050 raised to the power z divided by the second one, or actually the last one, the fourth one. So that would be 1.15 times 10 to the power negative 6 K, and then there it was 0.00100. Okay, so on the left you're going to get a 1 is equal to, now on the right what are you going to have So you can clearly see that I've actually done the opposite here. I've put the values that are bigger down, so it's going to be 1 over 2, because that one into there it's 1, there it's 2, so 1 over 2 to the power z. K's are going to cancel out, so this is the same as 1 is equal to, so if you're not comfortable dealing with fractions, put the bigger values on top. So this is going to be 2 to the power negative 1. Whenever we've got a fraction, whenever a number on the bottom goes to the top part, the power changes. If it's a negative, it becomes a positive. If it's a positive, it becomes a negative. Okay. So don't forget our z that is outside there. So therefore, we have 1 equal to 2 to the power negative z. Now 1 on the left, to ensure that we've got the same base, can be expressed as 2 to the power 0, so that we have 2 to the power negative z, and negative z being equal to 0 is thus z equal to 0. So we found the reaction orders in respect to all the three we had here. So obtain the reaction orders in respect to the reactants. There we are. So that is a 1, that is a 1, that is a 0. Find the rate constant. So if they ask for the lateral, it was going to be just the equation we add, now putting in the values. So H2O2, the power 1, and then iodide to the power 1 as well. And then finally h plus the power 0, which in that case will just be eliminated, so I won't even show it. Now to find the rate constant, how do we go about it? To find the rate constant, we have to substitute in the equation. Okay, just substitute in the equation any value, get any experiment of your choice. Okay, so let me go for experiment 1, right? Let me go for experiment 1. So our rate there was 1.15 times 10 to the power negative 6 for experiment 1. And then our K is what we're trying to find. H2O2 was 0.010. Iodide was also 0.010. So our goal is to find the value of K. So we can divide by the product of the two on both sides. So 0.010 times 0.010. Okay, so that will divide. So 0.010. So multiply what's on the bottom, divide that into what's on top. Our value of K becomes 0.0115. Okay, now it's a good idea to always indicate the units. So if you look at the overall order of the reaction, if you add all the powers, we add 1 plus 1 plus 0 is just 2. So the shortcut I use for finding the units is m to the power 1 minus n s to the power negative 1, where n denotes the overall order. So in this case, the overall order was a 2. So it will be like that. So it will be m negative 1 second negative. So these are the units for the K, and so we found the constant K as well. Okay.